So today is a webinar of a two-part series. Last week was the first one, which was a career guidance in geospatial data science for women specifically. And that was very cool. If you were not there, there will be a recording release sometime this week of that. We got to hear the career paths of a few women in geospatial that were just really inspiring. So highly recommend if you did not already watch that. And then today we will have a bit more of a technical series with talks around cloud-native geospatial and specifically cloud-native geospatial formats, software development, introduction, and AI integration. And so before we dive into those, I'm going to give a quick overview of the 4 organizations that are putting this on. Also, just so you know, my name is Michelle Roby. I am a developer advocate at Radiant Earth, which is the parent organization to Cloud-Native Geospatial Forum, also known as CNG. We are a geospatial organization of CNG, which is an initiative to collaborate with geospatial data practitioners to create vendor-neutral events, content, and education. So the idea is to kind of be the bridge between a lot of the education around cloud-native geospatial and those that need to use it or would benefit highly from cloud-native geospatial work. And we also just started a membership program, which will come with a lot of benefits throughout time as well. So if you're interested in that, check out our website. This is a guide to cloud-native geospatial formats. Christine is going to talk about those a lot today, and she'll reference this guide a lot. This was created in conjunction with Development Seed and through an asset impact project. So that's a really helpful tool if you're new to cloud-native geospatial in general. That's hosted on our site. You can always find it there for free. The next is Women Plus in Geospatial, which is a global professional network of more than 5,500 women, non-binary people over 149 countries. They have 3 main areas of focus, which is community building, mentorship program, and events and career development. If you're interested in learning more about Women Plus in Geospatial, you can find them on the internet, their socials, or their newsletter, and we can get these distributed so that you can sign up for those all. The next is Development Seed, which is an engineering and product company that is accelerating the application of Earth data to large global challenges. They leverage massive Earth data, cloud computing, geospatial AI, and they do product development for data scientists and empower decision-making with a clear and with our rapidly changing planet. A lot of Earth problems, as we all know, and Development Seed is doing great work to address a lot of those problems. If you're interested in learning more about Development Seed, you can visit them on their socials or their website as well. And the last organization that is helping put this event on is Element 84, which is a small business that works with public, private, and nonprofit clients to develop geospatial data processing pipelines, build software to also help address some of these big problems that our world and society faces today. Again, if you're interested in learning more about Element 84, you can follow them on socials or find them at their website. So today we have 3 really cool talks by each of these women. I'm listed here first. I'm the moderator, so I will be helping transition things. The first speaker we have is Lilly Thomas, who is a machine learning engineer at Development Seed, one of the organizations I mentioned earlier. And she'll be giving a talk on building blocks for software development. Next will be Christine Smit, who is a principal software engineer at Telophase, which is a NASA, I'm forgetting the word, contractor. And Christine's talk will be on cloud-native geospatial data formats. And then Tammy Glazer will be our last presenter, who is a senior applied data scientist at Microsoft AI for Good Lab. And Tammy's talk will be on geospatial AI. So the process will be each speaker will have about 15 minutes to give their talk, and we'll take all the questions at the end. So we should have up to 30 minutes for questions. If they finish earlier, then we will end earlier, or up to the half hour after. Depends on your time zone, but about an hour and 20 minutes from right now is when we'll end the webinar. But if you have questions throughout the presentations, I recommend putting them in the Q&A section of the chat. There should be a specific one outside the chat that it says Q&A. So please put your questions there. The more, if you can specifically address a panelist, that's easiest for when we go back to those questions, but we'll just collect those questions throughout the 3 talks, and then we can go through those questions at the end. And if we get to the Q&A section, you're also welcome to raise your hand and ask it using your voice, but ideally only during the Q&A section after all 3 of the panelists have finished. And this is just a reminder for on a webinar that we have actually next week at a little bit later time, but same day, Wednesday, just a technical introduction to cloud-native, cloud-native geo. And this will be, a little bit more basic and also include more information about the Cloud-Native Geospatial Forum. So with that, I'm going to stop sharing my screen and pass it over to Lilly.
All right, can everyone see my screen?
Yes.
Okay, super. All right. So yeah, it's a pleasure to be here today. My name is Lilly Thomas. Thanks, Michelle, for the introduction and also for introducing Development Seed. As she mentioned, I'm a machine learning engineer at Development Seed, which, yes, is an impact-driven organization where I get to work on a lot of challenges that I'm really passionate about. And I found my way into geospatial through an interest in learning how to study planetary scale challenges, and found that there's really no better way to do that than with Earth observation data. So I naturally discovered remote sensing and geospatial information science and studied those, and was fortunate to have a lot of really inspiring mentors over the last few years, over the last 8 years that I've been working in these fields. And they've really just consistently confirmed, that geospatial offers a lot of incredible tools and technologies for deriving insights about the Earth, and allowing us to really complement other fields of science. And so today I'm really excited to be joining so many brilliant women and to share some of my learnings. I'll be speaking about building blocks for software development. So hopefully it's not too dense, but without any further ado, let's get started. So today my talk and the slides are actually going to be adapted from a guide that I've developed in collaboration with a scientific journal called IEEE Geoscience and Remote Sensing Society. This guide's basically on best practices for science applied in industry. The guide itself is intended to serve as a resource for researchers and scientists and developers who are seeking knowledge and tools beneficial to executing science scalably within industry settings, with a particular focus on how to embrace open science practices effectively. I've aimed to make the contents address a growing demand for transparent, reproducible, and collaborative research approaches across various geospatial domains. Assumably, many of you are maybe academics or industry specialists, and both of these really entail climates where there's a high demand for expertise in data science, software development, and scalable computing. So the resources that I'll cover in the next few slides will hopefully provide a glimpse into some useful tech that's widely used today for geospatial. And the goal is really to impart some of those best practices for developing quality code for collaboration, managing large Earth observation data sets, scaling workflows, and integrating in a way that maximizes the impact and reach of your scientific efforts. As an engineer who programs in Python, I'll note that any of the software that I mentioned in the context of code development likely leverages the Python programming language. And this is particularly so for that which relates to the processing and analysis of raster data. Thus, anything I mentioned assumes basic familiarity with Python and geospatial data types. If you don't have a background in these things, there's a resource I'll show on the next slide that I highly recommend. This is a great online curriculum for upskilling in geospatial Python and fundamentals of raster data. It's hosted by the Carpentries, and it was created by colleagues at Development Seed. It's since been expanded by others in the open source community, so you can expect it to be really well maintained with respect to current methods. So during today's brief talk, I'll start with just a bit of discussion around the culture of openness, transparency, and collaboration within the scientific and software development communities. I'll mention some of those principles and the benefits of them and why I encourage the adoption of relevant methods and sharing of research outputs as much as possible. And then I'll color that with some of the current tools and platforms that support these principles, hopefully providing guidance on their selection and use. Just worth noting that these tools and platforms kind of exist on a spectrum in terms of general purpose use. Some are more software development agnostic, while others are highly specific to geospatial. So some might require more specialized knowledge than others. To learn more about open science and the adjacent terms like open source, open access, open data, I do really recommend this online curriculum. This is NASA's Transform to Open Science initiative. It's about a week-long course and provides a lot of content that really illustrates why this is a direction that we all need to learn about and consider. So to dive in, when software is developed in the open, we undergo this bittersweet experience of a constantly shifting technological landscape, which can imply like a lot of bandwidth to stay current, but the benefits reaped from openly contributed software really come down to the power of many minds working together to build solutions instead of only a select few, as is the case in proprietary software development. And it follows then that the open software development really does allow for a theoretically infinite number of stakeholders to contribute and validate new approaches, which, as you can imagine, is a massive accelerator for innovation. Expanding on that a bit more, I'll go over just a few reasons for choosing these kinds of tools instead of closed software. One is license costs. In the absence of these, fees can be reallocated towards development and compute. Coding is a lot more scalable than reliance on like a purely graphical solution, such as a desktop mapping software with built-in no-code tools. With open tools, you have a lot of options. Since they are free of cost, you can adopt as many as you desire or need. Repeatability and reproducibility. Open source code is public and transparent, so it's really easy for others to actually reproduce and validate methods, relevant methods. In terms of portability, usually open source code is a lot more amenable for cross-platform deployment than in like local or on-prem desktop environments, because a lot of individuals benefit from them. And so usually there's some scaffolding to support testing on various runtimes in virtual environments. So now I'll touch on the first building block really, which is some of the actual tools I'd recommend for scalable and collaborative software development. And as I'm sure you've gathered by now, the practice of enabling open access to both data and code allows other researchers and developers to scrutinize, verify, and build upon existing methods, which in turn really reinforces the credibility of new science and software. So jumping into some of the common platforms and associated protocols for collaborative software development, GitHub is a popular platform for publishing code and documentation. GitHub repositories such as this one, which was dedicated to the Scaling Science Guide content, so used to host relevant scripts and markdown files. GitHub allows developers to commit changes regularly to track the evolution of a code base over time. In GitHub, we almost always work from branches for new features or experimental changes so as not to affect the main code base. And the platform also features issue tracking and project management tools that can be used to coordinate tasks and communicate with co-developers. In GitHub, when you're setting up your software project, there's always a few files that you want to be sure to include, particularly when developing in the open. The first is a license file. This is because your inclusion of an appropriate license is essential for defining how others can actually use, modify, and redistribute your code. Some of the common ones are listed on this slide. You just want to choose one that clearly specifies the terms and conditions under which your code can be used. You want to document your project dependencies explicitly by maintaining an appropriate file that specifies packages and versions where necessary. You can use dependency management tools like pip or conda to install and manage these requisites consistently as things evolve. And a related practice is to use virtual environments, like isolated virtual environments by way of tools like virtualenv or conda to instantiate a specialized setup for running a software-related project. Using configuration files to centralize parameters and constants, this allows you to separate configuration details from code logic, which makes it easier to manage and update experiments or workflows without modifying otherwise static code itself. An example of this is the configuration file in YAML format that you see on this slide. It's structured for a simple image classification experiment, and within it you can really see that the architecture details as well as the training and testing parameters are all grouped and stratified in a way that makes the logic really clear. Some of the common ones are also listed on this slide. There's really, they all kind of suit different needs based on your workflows. Using version control systems is great. You could use Git to track changes, streamlining with other developers and manage code history. When you do this, you want to follow branching and merging strategies to organize contributions so that you can prevent conflicting changes amongst co-developers. You might also want to include a contribution and code of conduct markdown file, these two different files in your repositories, because these help outline guidelines for contributing to and citing your work. And on that note, it's also, as mentioned, really important to make sure you do that in a comprehensive way, not just citing your work, but also including these clear instructions on how others can use your code and the installation steps with examples. If you want to actually provide like a digital object identifier link, you can do this really easily for GitHub repositories via Zenodo, like you see here. This is an integration that we generated for the Scaling Science repository. In order to do something like this, you just need an institutional login or GitHub account, and the process is really simple. It just involves specifying some metadata about your repository, such as the title, description, authors, and keywords, and you can actually update the version of the repository in your citation via Zenodo as well. So moving away from GitHub and Zenodo, I'll close the discussion on platforms with Hugging Face, which is a platform that specializes in hosting and sharing machine learning models and data sets. And those are two things that we often work with in geospatial. You can use Hugging Face's datasets library to upload and share data. And similarly, you can use the Model Hub to host and share trained models along with associated code for implementation in GIST-like files called model cards. Moving on to the second building block, the Jupyter ecosystem. This consists of several tools and components that are designed to facilitate interactive computing, data analysis, and visualization, all of which we use a lot of in geospatial. So I'll go through some of the main affiliated tools and their purposes. Jupyter Notebook is an open source web app that allows users to create and share documents containing code, equations, visualizations, and descriptive texts. It supports numerous languages, as well as inline code execution, embedding of multimedia content, interactive plotting, parameter tuning, experiment tracking, and logging metrics. So it's pretty incredible. Jupyter Lab is a web-based interface that provides an integrated development environment for Jupyter notebooks. It also features code editors and terminals, and it has a lot of really powerful code editing features like code completion and debugging tools, syntax highlighting, and data viewers. Jupyter Book is a tool for building interactive, customizable web-based sites from Jupyter notebooks. That's what we actually use to build the Scaling Science Guide. And leverages all the tools that previously were mentioned for notebooks to build these HTML sites. Containerization, the third building block. These technologies are used to package code and dependencies into self-contained environments, and they're useful for ensuring that others can seamlessly run code with the same setup. Containerization is essentially the process of packaging your code with operating system, libraries, and dependencies necessary for creating a single lightweight executable called a container that runs consistently on any infrastructure. Most commonly, you'll find this done with a tool called Docker, which has garnered wide adoption due to its intuitive design. These are some benefits of containerization with Docker. We don't have time to go into all of these, so maybe at the end we can come back to this if it allows. But yeah, the process of creating, a Docker container is very simple. It starts with a Docker file, which is essentially a text file that contains instructions for the operating system, any dependencies to install, environment variables to set, and any commands to run once the container is launched. Without going into too much detail on this building block, as I believe it will be discussed in much greater detail in the next talk, I want to mention some open geospatial formats and analysis tools, as these two things really provide a path for interoperability and thus really are the drivers of productive code development on otherwise very heterogeneous and complex data sets that we witness in Earth observation fields. So STAC, which stands for Spatiotemporal Asset Catalog, is an open standard specification designed to organize and describe geospatial assets in a consistent manner. It's become a crucial development in the geospatial industry as it establishes a standard language and structure for describing geospatial data. Ultimately, we use STAC for indexing Earth observation data along with associated metadata for efficient search and access. One of the most useful aspects of STAC is the extent to which metadata can be made comprehensive. The possibility to include information such as image acquisition, spatial extent, cloud cover, resolution, and data format all really help with data acquisition because they allow for this really rich search criteria. STAC also accommodates evolving data collections and catalog structures by supporting versioning and incremental updates. It also enables data providers to manage changes to their data sets over time. And it really seamlessly integrates with the rest with existing geospatial tools and workflows by way of APIs and client libraries designed for interacting with STAC compliant catalogs. Open Data Cube is a software framework that facilitates management, analysis, and visualization of large volumes of Earth observation data, specifically designed to enable scalable, efficient, and consistent analysis of time series data across large geographic areas. And it organizes Earth observation data from various sources such as STAC into time series of multidimensional arrays, which we often refer to as data cubes, and allows you to combine data from different providers and sensors. It also integrates with machine learning and statistical libraries for modeling related analysis, as well as parallel processing tools like Desk, which makes it really well suited for handling large amounts of data. ODC Stack is a Python package extension for ODC designed to simplify the process of querying and processing data from STAC compliant APIs. Xarray is a Python library designed for working with the data cubes that we obtain from ODC and STAC, and it's particularly well suited for handling geospatial data due to its support for high dimensionality, coordinate metadata, and advanced array operations. And it integrates well with like very known libraries in data science like NumPy, Pandas, some newer ones like Polars and Dask. Raster.io, it's a core Python library that provides functionality for reading, writing, and manipulating geospatial raster data types and was designed to serve as a bridge between raster data and Python's scientific computing utilities. And then last one that I'll mention is Xarray, which is an extension of the Xarray library that adds geospatial capabilities for raster data processing. It really connects like the data manipulation features of Xarray with the spatial functionality provided by libraries like Raster.io or GDAL. I will close there. That was dense, and I hopefully that landed in some questions will come out of that, but I'll close there and pass it on to Michelle again.
Yeah, thank you so much, Lily. No, that was great. And I think it's like, yeah, even if it was a lot of information in a short time, we have it recorded so people can go back and like reference it. So no, I think that was perfect. And yeah, I have some questions. If people don't have questions, that I'll ask you at the end. So with that, I'll pass it off to Christine to talk about Cloud-Native Geospatial.
Hello. Hopefully you can see me. Let me share my screen. I have a cold today, so please forgive any coughing or other issues. Okay, great. So my name's Christine. I work for Telephase as a contractor for NASA. Um, and so how did I end up in geospatial? My educational background is all in engineering, and like my PhD research was in audio. So I have no educational background at all in the geosciences. But when I graduated 13 years ago, I had to find a job. And it just so happened that my brother's father in law knew that there was this geospatial opening. And so that's how I ended up here, kind of by accident. So 13 years ago, when I got started at an Earth Science archive at NASA, I was focusing on data processing and visualization. And then about 6 years ago, I shifted focus to cloud based serverless architecture and data processing, still at that same Earth Science archive called the JUSDisk at NASA. So I'm going to talk about a few things here. First of all, I'm going to start with some terminology because there's a lot of different terms that get thrown around that mean more or less the same thing. Then I'm going to talk about like where you can actually get live information that will stay up to date. Um, and then I'm going to actually nerd out just a little bit on like why data formats in the cloud need to actually be a bit different from the data formats that we've traditionally used on um, our own personal laptop devices. Then I'm going to talk about like how you design a data format for the cloud, and then I'm going to talk about some actual data formats that exist right now. So, first of all, some terminology. Because this is a relatively new field, there's a lot of different terms that people use that mean almost the same thing. So, if you hear cloud native or cloud optimized or cloud friendly or analysis ready cloud optimized, they're really all kind of getting at the same idea, which is data formats that are going to work well for you when your data is in the cloud. So, like, if you see all of these, just know they're basically the same thing. All right, so good information. This Cloud Native Geo Guide is really great. I highly recommend it. And it will be updated as new information comes in. So definitely this is a good place to start when you are thinking about moving your data into the cloud. All right, so this is a very new field, and a lot of times when I talk to people, I get a sense that they don't understand like why these data formats need to actually be different when you're in the cloud. So I'm going to try and give you like an actual picture of like why these things are a little bit different. So, traditionally you have, say, your laptop, or maybe, back in the day, you had, oops, sorry, back in the day, maybe you had a tower or a couple of servers. But the point is that the compute, which is the CPUs, and the storage, which is your drive, are like right next to each other. They are like physically right next to each other on this device. And what that means is that you end up with really fast communication over the motherboard of this device. But as we all know, you're kind of limited by how much storage you can actually stuff on this device and how much compute you can stuff on it. You can't just sort of scale infinitely. And particularly as data sets get larger, this can be a problem because you need to process things that can't fit locally on your device. So the cloud. Um, we have these like lovely icons. I'm using the icons from Amazon Web Services. And so if you're not familiar, the bucket refers to their data storage service called S3, and the orange square there is referring to their virtual machine or EC2 instance. But, the reality is that this is just actually software running on servers in huge server racks. And, these server racks, there's just tons and tons of them in like many, many warehouses. So when you see these like nice little diagrams of the cloud, what you have to remember is that this actually exists physically on Earth, not in the clouds, in these enormous warehouses scattered across the globe. So, like, if you want to have sort of a picture in your mind of what this means, it means that when you on your device communicate with that virtual machine, you have to do all that communication over a very long, slow network connection. And similarly, your compute in the cloud is making these sort of long, slow requests to the data server. So everything in this diagram is this long, tedious communication in comparison to the very fast communication that happens when you just are working on a single device. But the flip side is that there are lots, lots, and lots and lots of these servers. So you can scale your compute and you can work with these kind of almost arbitrarily large data sets, and you can get lots and lots of computation to work on that data. So in the cloud, the compute and the data are physically far apart, and that means that there's quite slow communication between those two parts of the system, but you get lots of storage and lots of compute that you can run in parallel. So because the communication and the access to storage is so different in these two cases, you really have to kind of start thinking about setting up your data storage differently to take advantage of the strengths of the cloud and minimize the weaknesses. So the first optimization that you want to think about is only fetch the data you need. Don't go and fetch the entire globe worth of data when all you're interested in potentially is, say, a couple of areas with where there are hurricanes that you're interested in looking at. Now, I had to prepare these slides in advance. They have to go through an approval process. So when I submitted these, the two hurricanes that we were interested in were Hurricane John in Mexico and Hurricane Helene hitting Florida. So here we are, unfortunately, already out of date after only a couple of weeks. Um, so when you fetch data and you want to fetch the data you need, what that means is that your data format needs to have kind of addressable chunks or tiling that you can get individually so you don't have to pull over the entire file at once. Um, then the sort of the second optimization that you need to think about is making metadata easy. So, a file format fundamentally, like before you actually open it, all you know about it is maybe its size, right? And you can think of it sort of as this array of zeros and ones. So you don't know what's in there. So you can't get the chunks because you don't know where the chunks are. So the metadata that you need to know in order to efficiently access that data is first of all, like what data is in there, like if there's multidimensional arrays, like what they are, and then for those arrays, where the chunks exist in the file so that you can just pull those individual chunks. So the sort of second format requirement is that you need to consolidate that metadata for the chunks and tiles so that the tools using that metadata can just make one request, get all the metadata, and then from there just get the individual tiles or chunks that they need for the computation. So that's really it. And if you look in other places when they talk about this, they might sort of word things slightly differently, but these are the two sort of basic issues that you need to think about. So let's talk about some actual data formats. Um, and again, we're going to be using this Cloud-Native Geo Guide here. So it has some really nice questions that you want to ask yourself when you are thinking about moving data into the cloud. And so the first is, what variables should be included in the new data format? Don't move things that you don't care about. Um, are you going to be creating copies to optimize for different needs? So as you read through this guide, you'll find that some data formats work for better for different kinds of uses. So you might end up making multiple copies of the same data. What is your intended use case? What is the expected access method? How is your data going to be rendered? These are all some questions that you want to have in your mind when you're thinking about moving data into the cloud. Now, I really want to emphasize this. This is all still quite new and it's all changing very rapidly. So anything I tell you today is potentially going to be out of date, tomorrow or a month from now, and almost certainly a year from now. So I encourage you to go back to that Cloud-Native Geospatial website to keep up to date. So I'm going to use their table, which is a really nice summary of sort of a lot of the traditional file formats versus what you might use in the cloud. And then I'm going to go through, focus in on a few of these here, and I'm shamelessly going to pick the ones that I know best. But for the other ones that look, if they look interesting to you, definitely go to that Cloud-Native Geospatial page. So GeoParquet. GeoParquet is basically Apache Parquet, which is a cloud-native data format with additional special metadata that allows you to specify points, lines, polygons, etc. Um, in the file. You're also able to specify CRS so that tools know how to geolocate this data. The one issue that you may run into with Parquet files is that the large files can get quite cumbersome. Like if you try to put, a couple terabytes of data in that, it can be hard to manage, particularly if you're trying to update things. This format is useful for shapes, for anything that you might put in a GeoJSON, and point data. So next, we're going to talk about cloud optimized GeoTIFF. So if you're working with raster data, you're probably familiar with GeoTIFF. And COGs are just GeoTIFF with consolidated metadata. This means that it's backwards compatible with all your favorite tools. And so if you are right now creating GeoTIFFs, I highly recommend that you just make COGs, because then they'll be useful regardless of where you store them. And again, this is good for raster data. Czar. So this one is particularly near and dear to my heart because I use it all the time. It has essentially the same data model as HDF, if you are familiar with that. It's multidimensional arrays and metadata. Czar really shines when you have very, 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 very enormously large multidimensional arrays. Um, the nice thing about Czar is that um, you can update these large arrays quite easily, unlike with Parquet. But it can be tricky to manage those updates if you're trying to update a data set that has sort of multiple readers and writers at the same time, because Czar actually splits up your array into multiple objects. But this is good for multidimensional arrays and really anything that you would have perhaps previously stored in HDF or NetCDF. All right, so there's one thing on here that maybe looks a little odd because it's not an actual file format. It says references in Kerchunk. So what is that about? Um, well, these two formatting rules that I was talking about earlier, the addressable chunks and consolidating the metadata for chunks and tiles. If you are familiar with some of these traditional file formats, you may be saying to yourself, why is she talking about chunks? HDF has chunks, NetCDF has chunks, there's already chunking. The issue is the consolidated metadata. Traditionally, these file formats, their metadata is kind of scattered throughout the file. And so when you're trying to pull this metadata, you end up having to make multiple of those long, tedious network requests to get the metadata. And of course, this is the original GeoTIFF, not the cloud optimized GeoTIFF. So somebody came along and said, well, the problem I need to solve is just this consolidated metadata. Why don't I just create a separate metadata file so that I can take advantage of the chunking that already exists in these files? And that's really what Kerchunk is. It makes your existing data files cloud optimized so you don't have to make copies. It's compatible with a lot of the sort of ecosystem that's already out there around Czar. Um, the one of the limitations, though, is you are going to be limited by the existing chunking in the files. So this just describes the chunking. It doesn't change the chunking. But this is a really excellent way of making your existing raster and data cube data perform a lot better in the cloud. All right, and so again, remember that all of this is sort of changing as we speak. People are coming through with new data formats or new ideas for working with traditional file formats. So when you undertake a project to start running things in the cloud, I highly recommend, going and taking a look at that reference before you do anything. And then I just had a few thanks. Where I got some of my, lovely clip art. And I'd also like to think that the Cloud Optimized Geospatial Formats Guide, it really has a lot of really good information consolidated together. And some of the other engineers I've worked with at the JustDisk on data in the cloud, particularly Hailiang and Dumai. And that is the end of my presentation. I'll hand it back to Michelle.
Cool. Thank you so much, Christine. That was really great. And I think often, like, when things get more technical, we kind of forget about the why. And so that was super helpful to have in there. So thank you. And then we'll pass it off to Tammy to finish us off.
Awesome. Thank you. Let me share here. Are you able to see my screen, my slides? Perfect. So thanks, Michelle, and thanks everyone for being here. This is a really awesome event. I'm really excited to get to know this community better. My name is Tammy Glazer. I'm a senior applied data scientist with the Microsoft AI for Good Lab, and most of my focus is on using geospatial and remote sensing with AI to learn about the world. Great. So how did I get here? I showed the slide to really reinforce that my path has not been linear by any means, and I think that's a common theme among people who work in geospatial. There's a lot of different ways to sort of navigate this career. The early part of my career was really focused on public policy, international development. I worked on President Obama's Feed the Future initiative, and when I was working on that, I was primarily involved in large household surveys and impact assessments of agriculture and nutrition programming in sub-Saharan Africa. And it was really when I was doing that work, I had a bit of a background in econometrics and statistics, that I was like, how do we measure these same phenomena in places where we don't have survey data? What other data sources are available to learn about the world besides just household surveys? And that's what really sparked my interest in geospatial. I worked for a few years at Tableau, which is a data visualization software company, and that's where I really honed my interest in visualizing data in a lot of different ways. I eventually went back to grad school, studied computer science and public policy. I worked at an organization called Driven Data that hosts large-scale machine learning competitions for social good, and really brought all of those different interests together to where I am now with the AI for Good Lab. And so really there's many ways to navigate this field. And I also want to show this because I do a lot of hiking and backpacking personally, and I love looking at maps. It's like one of my favorite parts of it. And I was like, how can I incorporate maps into my day-to-day job? And so with the AI for Good Lab, we're a team that leverages AI and data science to address some of the world's great challenges. It's a team of data scientists and economists and data storytellers from around the world. And we partner, importantly, with subject matter experts from academia, nonprofits, and governments to work on these different projects. So often we're not the subject matter experts, but we're applying the methods to important problems. And so really what I think about a lot is how can geospatial AI help us to understand the Earth and its inhabitants? And so there's a lot of remotely sensed data that's being collected all of the time. There's, stratospheric balloons collecting data. There's satellites. There's UAVs. There's all of these different data sources, and there's more and more every single day. And so really, there's more than 1,000 satellites that orbit the planet, collecting Earth observation data. And these create, as has been discussed in the earlier presentations, petabyte scale time series data sets that are massive and difficult to work with. They can be used to address global scale challenges from climate change to food insecurity. But we need tools to be able to work with this data. And so AI allows us to integrate and analyze these enormous data sets, and it helps us to transform how we understand and interact with the world. And so I like this quote from the UN Office for the Coordination of Humanitarian Affairs, that finding ways to make big data useful to humanitarian decision makers is one of the great challenges and opportunities of the network age. And this goes beyond just humanitarian organizations. And so, as I've sort of alluded to, the way that AI can help here is that it helps us, look at data at a large geographic and temporal scale. It also helps with data integration. So how can we combine and leverage multispectral, multimodal data sets and put this all together to learn about the world? Efficiency is an important thing here as well. So, something you'll hear about is sort of pre-trained models that have been trained on a lot of data that we can then leverage and then specialize on a certain task. And so that helps to make our pipelines more efficient. AI helps with pattern detection. So often, we're talking about visual imagery, but there's also data that's not really visual, and how can we detect subtle patterns in that might not necessarily be obvious to the eye. And finally, I think about real-time insights. So can we have alerts, early warnings, things like that to help us reduce our time to action? And so sort of more broadly, when we're talking about AI, I think about it sort of in these ways. There's predictive modeling, so learning about the future. There's detection, so object detection, anomaly detection, change detection. There's damage assessment, so looking at before and after and what has changed between those two images. Pattern recognition, classification, measurement. So these are like the types of tasks that you can do with AI. And in a little bit, I'm going to go into specific examples, but what you'll notice across all the examples that I talk about, it's really always this pipeline. So you start with some sort of imagery or data input. You have some sort of training data, so something on the ground that's been measured, whether that's the outline of a building, a soil sample, it could be really anything, but how do we connect that sort of geospatial input with something that's physically happening on the ground? You apply some sort of a machine learning algorithm to that, connecting the two, and that generates geographic insights. And so here's just sort of a general example that comes from my own work. I do a lot of work on understanding populations, population movement, and building density and how that's changing over time. And so in this example, you have some sort of an image, you pair it with building footprints. And then you apply a deep learning model to that. And then for each pixel or actual space on the ground in new areas, you can start to predict what do we think the building density is based on the imagery in that area. So this is sort of a real example of what that pipeline might look like. I think it's important, and this I think is the last section before I really dive into a few examples about what sets geospatial AI apart from just AI generally. And so I really like this position paper that a few of my colleagues put out. And one of the quotes that I pull from here is that satellite data constitutes a distinct modality for machine learning. We must recognize it as such to advance the quality and impact of SAT-ML research. And so, as has been talked about, when we're talking about geospatial data, it's information associated with locations on Earth. And that can come in a lot of formats, vector formats, points, lines, polygons, but also raster formats, which is a grid of pixels where each pixel has a value that's saved in one of the formats that was just talked about. And working with geospatial data sets is very tricky. It's tricky for everybody. Even if you've been in this field for 20 years, it's still really tricky. There's a lot of instruments, and there's always new instruments that are being sort of deployed that have, output data in different formats. When you pull data, you have to think about how to crop it correctly. Often you're dealing with multispectral imagery, so different kinds of channels and inputs that you're bringing together. There's temporal variation, there's different resolution of imagery, different coordinate reference systems, and then of course the volume. And so when you bring all of this together, often a lot of your time is really spent in the preparing of the data and merging it and getting it sort of analysis ready. And that final step is applying some sort of a model to it. And that's often a lot less of your time than you think it'll be. But with that, it is really exciting to see all the pieces come together in some real ways. So I wanted to share some of the applications that I work with, and feel free to ask questions. There's a lot more than what I'm sharing here. So one of the areas in geospatial AI that I think is really exciting is in the space of disaster preparedness and response. So here's a few sort of examples of what I mean by that. You can use AI to map building footprints from aerial imagery to understand where people live for different disaster risk management applications. You can do things like analyzing satellite data of rainfall, land use, topography to predict floods, provide early warnings in different places. You can do things like mapping changes in temperature and smoke signatures to detect and monitor wildfires in real time. And so, here's a real example, something that our lab works on quite a bit, which is building damage assessment. And so in the Turkey earthquakes, but basically when these earthquakes happen, we acquired high resolution satellite imagery from a few days before and then 3 days after the earthquake to assess building damage and what had changed in that time. And so when we do these workflows, what's really happening is we get the imagery. We actually have people on our team who are looking at it before and after, outlining what looks like damaged areas. And then if we do that for, let's say 100, even just like 100 samples, you can then take that and train a model on that and run it over a larger area to then detect other damaged buildings in that area. And so we do this in a really short amount of time to try to get a sense of how many buildings have been damaged. And we partner with governments to share that kind of data. Here's another real world example of an application, so flood risk assessment in India. So for this project, we partnered with SEEDS, which is an organization that is building community resilience in low income areas in India. And traditionally, when you do some sort of a risk assessment, you're using disconnected data sets. You're using, tabular data, looking at elevation data, population data, and this can be pretty difficult to scale. And so for this project, we combined AI with satellite imagery to detect buildings, to try to classify rooftop materials in these areas, find areas that might be high risk, and also look at historical flooding and bring all of those factors together to create these sort of risk maps that could be shared with community leaders to help prepare for flooding. And so this allowed the communities within which we were working to help design evacuation routes, to reinforce buildings, to improve water and sanitation management. And so, here's another type of example. I'm going to fly through these. We could talk for really like an hour about each of these, probably longer, but I just want to kind of give a high-level survey of the types of applications. So another space outside of disaster response is environmental conservation. So Arizona State University is mapping the world's coral reefs to monitor threats to support biodiversity and coastal protection with the Allen Coral Atlas, which is a really cool project. I encourage you to check that out. Another example here, Global Fishing Watch is using AI to predict illegal fishing activities from GPS-based signals shared by vessels. And the World Resources Institute is monitoring sudden loss of tree canopy cover, alerting us of suspected deforestation. So these are like some examples of environmental conservation applications. This is, just to go in a little bit more detail, the Global Renewables Watch is a project that our lab is working on, which really the goal here is mapping the world's utility scale solar and wind installations, because we don't really have a sense at a country level of our progress towards different renewable energy goals. And so if we can get a sense of how much renewable energy is being generated, what is the capacity of different countries by looking at it from above, that helps us to really understand our progress to different emission, net zero emission, that type of a goal. And but at the same time, renewable infrastructure requires land use, which has a separate set of environmental impacts. And so by developing a tool where we map these things and take a look at both the land use and the large scale installations, this allows us to evaluate clean energy progress, capacities, and gaps. Another bucket of areas is agriculture and food security. So the Catholic Relief Services is applying machine learning to forecast household food insecurity up to 4 months out. Microsoft is working with Kenya's Ministry of Health to forecast malnutrition in Kenya. The list kind of goes on and on. I'll just highlight, this one I think is an interesting application, which is around land cover maps in Kenya. So another project that our group is working on is looking at if we can help smallholder farmers in Kenya map coffee producing land to ensure that the Kenyan coffee remains eligible for export, because there's been recently some regulation that's blocking imports of coffee into Europe that has been produced on deforested land. But often it's hard to really attribute where did that coffee come from in the supply chain. It can be complicated. It's not always straightforward. And so what can we learn about this supply chain from above so that we could say, yes, this coffee was not produced on deforested land and therefore can still be imported into Europe. And so just visually what this looks like. is, here's a map. And then if we run a model on top of it, you can actually segment at a very granular level, what is that land being used for? And so you can, safely attribute that coffee to a specific parcel of land. And so I'm not going to keep going. Like there's a lot. We'll share the slides, or it can go more on and on. But just at a high level, climate change mitigation is another really important area where you can use geospatial AI, looking at population trends. And this is a project that I've been working on for the last year. So at another point, maybe we can go a little bit deeper into that. And then the last one here, I think is really cool, is actually starting to look at historical imagery and georeferencing that. And what can we learn about the distant past outside of when we were necessarily flying satellites, but just if you have any imagery, can we use this whole breadth of knowledge to learn about, the past using just regular aerial photography? And so really backing out of all of that, I hope the message that you sort of take away is that geospatial AI is inherently cross-disciplinary. You really need subject matter experts in all of these different areas. You need computer scientists, you need demographers, you need environmental scientists. And so I really, where to start, I encourage you to figure out what part of that whole process interests you. If there's a specific part, domain focus that is interesting to you, I would go deep into that. There's also the whole data science pipeline, from the data acquisition to the prep, to the modeling, to the visualization and storytelling. So try to figure out if there's a part of that pipeline that interests you and go in that direction, because there's a lot of ways to get involved. I'm, really happy that everyone talked about the open source tooling available. I'd say a lot of what I've learned in this field has come from that community. Reviewing other people's code is a really, really good way to learn. So if you even just look at open source repositories, and often things will be tagged as like an easy first issue to tackle, that's a good way to kind of get started and learn these different tools. There's a lot of great online courses. I'm happy to make recommendations there. I also think that participating in online machine learning competitions is a really fun way to get started. And there's also prize money that comes along with that. So good incentive. And then really just joining online communities like this and Women in Data Science. I think there's a lot of great resources out there, and just talking to people is often the best way to get started. And yeah, I think that's it for me. So thank you so much.
Amazing, thank you. No, that was amazing. And generate a lot of questions. Maybe we'll start chronologically, give you a little bit of a break. There was a question for Lilly. So in the chat, someone's asking how to stay up to date with the abundance of open source libraries and model architectures coming online. How do you evaluate trade-offs between adopting a new method or sticking with what you know? Really good question.
That's a really great question, and something that we're always faced with. It's definitely something that I contend with and my team does. There's no one way to really go about it. I think as for myself, in the past, the way that I have stayed up to date with new tools that are worth considering has been through different online forums, whether that's like X or LinkedIn, different blogs that I've followed, how people are doing things, people that I know in the community, co-developers, really watching, the approaches that they're embracing. And essentially there's a form of a peer review process that vets these new tools at some point or another, and really illustrates the pros and cons. So ultimately, I think it's always keep an open mind to new tools, to incorporate it in your tech stack. But most certainly, I think just adopting a new tool because it's made available is not really a good reason. I think oftentimes like that, you can hit a state of like paralysis by analysis by the number of options that you actually do have when you're using open tools. And the trade-off really with open tools is that there's oftentimes there's like a lot of upskilling that is that actually is entailed for adopting these new tools, and they may have different syntax, they may have different programming structures, and all of those things require time to actually learn before actually integrating them into your workflow. So doing this, this analysis of the amount of time it takes to actually adopt a new tool and what are the actual net benefits you'll get from it, is something that you just learn over time. It's not very straightforward, but keep an open mind, but definitely don't be overwhelmed by the plethora of options and the speed at which things, and this is, I think, just to close on this answer, as both of the other panelists have mentioned, this landscape is moving very quickly and really does make you feel as though you need to be on top of everything. And I would just say, take that in stride. The things that are really, pivotal and groundbreaking will surface at one point or another, and they'll persist. So, yeah, don't get too caught up in the noise of all of the new tools that you have available to you.
No, I think that's great. And I feel that way a lot too. So like this question really resonated with me, and of like, okay, well, how am I supposed to get better on this? There's always new stuff. But it's interesting because a couple of the packages or tools that you mentioned in your presentation are ones that I've seen in school like 7 years ago. Like there's certain foundational ones that are always like still useful, at least I will say. Maybe not won't always be useful, but kind of getting that foundation and ones that have been around for a while. And then maybe once you feel comfortable with those, moving on to these like shiny new tools in the future.
Exactly. Yeah.
Do any of the other panelists have anything to say on that one?
I completely agree with everything Lily said. I think there are certain moments when you are looking to solve a problem, and that is kind of the moment when you go out there and you say, okay, what is available? And maybe you talk to people maybe you go to forums where you've gotten good information before, and then you make a decision. So where I work, we sometimes have something called a bake-off, where if we can't sort of agree on like which technology we're going to use, everybody gets a day to throw something together and try to show us like how well their version works, and then we kind of go from there, which works nicely if you have a large enough group to handle that. But once you are in the middle of building, you can't just rebuild the entire thing every 2 weeks. Like it's not, so then you get to that trade-off of when do you decide that it's time for a refactor.
Yeah, I mean, I totally agree. I think that you often will look for a new tool if you're hitting an actual problem. Like you're not able to solve something with the current tool, and then it is a good practice to kind of zoom out and say, what else might be out there? Maybe somebody has thought about this problem before and I don't need to fix it from scratch, and there is a tool. But I don't think it really makes sense to just constantly be switching your tools just for the sake of it. As long as you can get your task done with what you know, that's often good enough. And yeah, I wouldn't, it sort of happen naturally when you hit roadblocks, then you'll start to say, okay, what else is out there?
No, that's great. Thank you all of you for that. Okay, the next question was specifically for Tammy around tools and software. So someone's asking what tools and softwares you use in these analysis.
Yeah, really, it's the tools that have been talked about today. I'm a huge fan of the open source community and contributing to it and using software that comes from it. So I'm, programming in Python. I'm using things like Xarray and Czar and all the fun packages that have been talked about. Because I'm working at Microsoft, I'm often plugged into the Azure tech stack. Before my time at Microsoft, I used also, AWS and other types of, cloud platforms and stacks. And so I think what's really important is often it's more about learning the concepts and often the specific syntax. It's a smaller learning curve to switch between one platform and another. It's more about what is it that you're trying to accomplish, and it's more about the concepts than the exact tooling, I would say. But generally, I'm working within the Python ecosystem.
Cool. Thank you. Okay, so we're getting into some more specific ones around AI. There's a chunk for you, Tammy. So yeah. So someone is working on a project creating a Geo AI platform for monitoring and optimizing green spaces in Nairobi. And they're having a problem with doing the real-time monitoring, and they're stuck. Do you have any perspective?
Yeah, no, it's a good question. Often easier said than done, and real time it's a tough term to actually implement. It's often near real time, or there could be some sort of a delay. It doesn't always mean that it's like an instant alert. But I think what's important here is identifying the specific triggers that you can actually act upon and setting up something that actually alerts you or signifies that that trigger has been met. So specifically, I'm often using, like I said, with Azure, within that ecosystem, Azure machine learning, you can set up sort of automated alerts based on when certain criteria have been met. But I would say for me, often the bottleneck in this and the challenging part that totally resonates and I can connect with is often the acquisition of the imagery, actually getting the new imagery and starting, once you have that, starting the pipeline is pretty straightforward. But getting the imagery could take a couple of days. And so even when I was talking about sort of like the building damage assessment work, that can be a challenge. It's really not always instant access to that imagery. So I'm happy to, I could put in the chat maybe some more specific like tools, but yeah, it's my advice here is just figuring out the very specific thing that you can act upon and setting up any sort of triggers based around that.
Well, that's great. Thank you. And then the next one that was for you as well was, how often do you create a full training data set for your application? And how often do you use foundation models or pre-trained models? And what architectures do you use most often?
Yeah, that's a big question, a good one though, and I'm also interested to hear from the other speakers on this. But I would say on the training data set front, I definitely always start a project by looking at what training data is already available. So, looking at Source Cooperative is a really good resource for that, hosted by Radiant Earth. And seeing what training data has already been created and then doing an analysis on that data about what is the geographic representation of that data set, what groups maybe aren't included in that might be important to the application that I'm about to build or do. And so really having an understanding of, can we use what exists, or do we need to maybe even hand label new data? So it's kind of a combination of both. Like there's always some aspect of using something that exists and then often adding additional data to that or sending someone out to capture new data. It really just depends on the application. So it's sort of a combination of both. And how often do you use foundation models, pre-trained models? I think, a lot of this is around experimentation. So it's actually empirically seeing what is helping with your modeling. So we'll often try using pre-trained models. But in my presentation, I kind of talked about how geospatial data is a distinct modality, and a lot of pre-trained models, and this is starting to change, which is really exciting. But traditionally, a lot of computer vision pre-trained models are trained on, pictures of cats and dogs and things that aren't geospatial, and we try to adapt those to a geospatial context, and they don't work that well. It might be better than starting from scratch, but often it's introducing a lot of noise. And so now there's this really exciting push towards geospatial foundation models, which I am definitely following along with. I haven't been using them a lot yet, but I think that is sort of the next step, the next frontier. I don't know if I captured all of it.
Any other panelists have any perspective on this? If not, the next one is a group question.
Oh no, I agree with all of the points. I think what's really interesting right now is like how do we use these foundation models? They're being developed and they're being shared. There's still, I think, some ambiguity on how to actually leverage them and really like identifying what those reasons are for using them. And really, I think it comes down to these foundation models are intended to capture semantics that are generalizable across many domains. So for example, if your data that you're using to supervise the training of a model is very sparse, or you know, leveraging a very diverse geography with a lot of different nuances, then these foundation models have captured a lot of the semantics. If they've been trained on modalities that are relevant to your problem, they've captured a lot of semantics that otherwise you would have to learn, that your model would have to learn from scratch. So sparsity of data or complexity of data, these are things where you would reach for a foundation model that is captured, an understanding of the data that's relevant for your problem, instead of training a model from scratch. So that's a good use case for them, and that's what we're really trying to demonstrate when we develop these foundation models for Earth observation.
Awesome. Thank you, both of you. So the next, there's two questions that are similar, so I'm combining them. People are curious who might be just entering the geospatial field or curious about things outside the geospatial field, like Tammy had mentioned with AI. There's, it's always in conjunction with something else for geo AI. So if someone doesn't know what interests them within the geospatial field or outside of it, like how do they, any advice on determining what interests someone more, what works better for them? Someone said, I feel I'm flexible and I can go into most sectors, but I don't want to be not specialized enough. So any advice on the diving into one thing deep versus generalization, like advice across the board on those sorts of things?
I mean, I think internships are actually a great way to figure out what you want to do. I did a lot of internships when I was an undergraduate and discovered all the things I didn't want to do. So, and in engineering, you tend to get paid for them, which is great. And you get networking opportunities and you learn a lot about how different kinds of academic versus government versus commercial sectors work. So I highly recommend internships.
Yeah, maybe one thing I can add is if for those individuals on this call who are still in school or in grad school, taking courses completely outside of your, I shouldn't say completely outside, but like that seem kind of random maybe to your specific focus area can be pretty inspiring, or maybe figure out you don't like that. So as a quick example, like when I'd say the first computer vision course that I took was a radiology course. And so it was applying like similar techniques, machine learning, AI, computer vision to medical imaging. And I'd say a lot of the skills that I'm using today are things that I learned in that course. But I learned, okay, that's not exactly like the area for me, but it opened my eyes to like the possibilities and to methods. And that was completely outside of what I was studying, but I just thought it sounded cool. So just take often, look at the courses available if you are still in school and see if any might be like similar to what you're studying, but just a little bit different.
I think the only thing I would add is that starting somewhere is great. And I think once you really find yourself, it's a small industry. Geospatial is a really small industry to begin with, I think. Yeah, engaging with the community, I think, is one thing that really shows you all of the different ways to work within this space, all the different challenges that you can solve. That was eye-opening for me, to observe how other people are doing things. And yeah, I think that there's a lot of power within community, especially since this is so small, so niche still, that's learning through others. and in practice and doing, I think is a great way to get started as well.
Yeah, I think all of those answers are great. And I'll just add, when you're going through these processes and trying different things out, just doing your best to be in tune with yourself and figuring out like what you genuinely are enjoying or not, can be really insightful. Yeah, it's like great to do lots of different things, and then you want to be able to be honest with yourself in those processes and figure out, yeah, what feels good, and then also what natural skill sets that you already have, and like where you feel like you're actually utilizing your natural skill sets, because each of you have very good natural skill sets, and they might just look different than your coworker or your friend or your sibling. So yeah, just being honest in that sense, and there's a right path with whatever skill set you have naturally, and like try and figure out how you can build that up instead of trying to build skills. Like there's a AWS has this concept a lot of like working on building up people's strengths and instead of their weaknesses. And yeah, and so I mean, there's different ways you can go about that. There's nothing wrong with like trying to get better at something you don't already know, but kind of figuring out like what are the things I love to do and what am I really more skilled at naturally, and then just trying to like kind of dive into those, I think makes work more fun. Okay, the next question, there's a lot, I'm like worried we're probably not gonna get to all of them. So I'm trying to kind of be selective, but I haven't picked the next one out yet. One just kind of general one of for AI, or what are the most challenging projects you have to work with, you've had working with AI?
I don't think necessarily naming a project will be helpful, but I think like a general area that is very challenging is when you're doing anything that is supposed to be global in scale, or looking at, many years of imagery, like generalizing in that way is almost like near impossible. It's very hard to have a single model that works exactly in the same way in every part of the world, with different types of topographies, different landscapes. Often imagery is coming from different timestamps. And so I think what really helps here, and I know this is not a very specific project, but it's just a theme that I've run into, where if you're looking in one area, I find it a lot easier than trying to make like a globally generalizable model. And so I think it's really important to have know like how to evaluate your models, and to have sort of what I would call holdout sets of data that is not included in your model training, that you can evaluate on to understand performance in different types of contexts. And so I think that, yeah, that's just like something that is always challenging if you're trying to do something at global scale.
Yeah, no, I've seen that happen a lot too, or yeah, it's a big world. Okay, the next one that I wanted to address was I've seen there's another one that's similar, so I'm gonna kind of combine them of what key software development skills are necessary to land a job in any of the places that you work, and like beyond expertise in deep learning, geospatial analysis, and Python. And someone else had asked about yeah, like what technical skills have you all developed that felt like they're fundamental in you landing your current jobs? So just insight on, and some of you have touched on these throughout your talks, but just kind of reemphasizing like the foundational places to start with getting a job, and specifically like the jobs that you all have now. What were like the key things that helped you get those jobs?
Since there's software mentioned, I think that it really depends on ultimately what you want to do within geospatial. If you want to do AI, machine learning, I think there are some things that we've all converged on. A lot of us are writing in Python. The actual machine learning framework that we use does shift, but right now for a while it's really kind of centered on PyTorch. These things will change, and I wouldn't qualify them as, things that you have to know in order to get a job as a machine learning engineer in geospatial, but these are like soft recommendations. I do think some are weighed a bit more heavily than others. Like Python is something that you'll find most people using these days for scientific computing. Aside from tools themselves, because those change so rapidly, I do think understanding data types for the field that you're interested is probably the most critical thing. Understanding data types and how different sensors and configurations are used to address different challenges, and how to actually work with these and read and write them and manipulate them in Python, I think is and the same goes for, I mentioned raster data a lot, but the same goes for vector data, of course, how to work with this type of data. Those are probably, understanding also how to scale things and, is important, because this data is often very large compared to other fields. These are probably more tool agnostic by, core technical proficiencies, I think, that will give you the most mileage in this domain.
One concept I might add is, and I saw this in one of the slides. I saw cookie cutter in one of the slides, and I think again, that's tool agnostic, but are you developing pipelines, or if you're starting to write code, like, can other people figure out what's going on without you being there to explain it? And there are some really great frameworks like Cookie Cutter and Cookie Cutter Data Science that are sort of organizationally ways to set up repositories and set up your code so that people know where to find things, no matter whether they've talked to you or read your code before. It's kind of standards around organization and commenting and doc strings and all of that stuff that can sound really boring. I think it's really important, especially in getting that first job, because you'll need to show a code sample. And so thinking about that up front, I think, is really important. It's something that I often look for. Just, are you explaining what you're doing? Are you commenting? And is it something that I could reproduce if I needed to?
So NASA and AI is a little different. And where I work at a science data archive. And so our job is to kind of give data to people who will then maybe use AI applications on the data. But I would just say, in terms of getting hired as a developer somewhere, now that I've been more on the side of doing on some of the hiring end of things, having, it sounds crazy, but having a resume that is readable. Like, sometimes we get people like, why are you giving me 5 pages and you've been in the workforce for 2 years? Like, what is this? Um, so some of the basics that you heard about years ago in terms of getting a job, having a readable resume, being able to communicate well, honesty. So, like, if someone asks you, "Do you know about X?" and you don't know about X, it's okay to say you don't know about X, and, like, don't try to, um, tell people what your knowledge is beyond what it actually is. Um, in a lot of these jobs, the reality is that you're gonna learn a lot on the job anyway, because you're gonna be working with data sets maybe that you haven't worked with before, or working in um a process that isn't exactly the same process you've had before. So a lot of what people are looking for is like, have you learned new things? Can you learn things once you come here? Are you going to be pleasant to work with? Like, some of those, sort of more fundamental skills are also quite important.
Awesome. So there's 1 minute left. So the final question that we'll have, I'm sorry for those that we didn't get to. Feel free to reach out to people after, or you can reach out to the organizations to see if you can get your question answered. But the general one that I'll finish on is two people asking around how to keep posted and aware of all the advances in tools, emerging topics in geospatial, and then the other one regarding questions about how to find jobs and whatnot. All of the organizations that we listed today and we linked to their social medias. We'll send out that information after as well. So following organizations that you're interested in, we put out a lot of blog posts about tech. I know a lot of people from the organizations listed today are putting out blog posts around emerging tech. And for internships or mentorships, there's the Women Plus in Geospatial and other opportunities around this sort of work. Do any of you have additional advice for keeping up to date on things and getting connected in the geospatial community?
I mean, I love SciPy. So, SciPy is an annual conference. It's amazing. You meet a lot of the people who are committers on these like core libraries that we're all using. Now, if you there's certain kinds of jobs where you tend to go to conferences. So if you are not in a position to go to conferences, SciPy does publish all of their talks on YouTube every year, and so that can be a nice way to see what people are thinking about.
Yeah, conference papers are usually a bit more digestible to read because they're smaller, and those are outcomes of these conferences as well. Just keeping an eye on, maybe identify some science conferences that are relevant to the direction you want to go, and just keep an eye out for the conference papers that come from that or the abstracts, and you'll get a pulse on really what people are interested in studying and how they're doing that. I think that's a great way, to go off of that.
Yeah, one, I guess a specific plug I can give, a way that I personally stay up to date on some of the AI deep learning side of things within geospatial is there's this resource called Satellite Image Deep Learning. It's like a website.com, or there's also a GitHub associated with it, maintained by Robin Cole, and it's just like there's always like every day new tutorials and links to papers and things being posted there. So that's like a way I personally stay and connected and involved, and I'm sure there's many others like it. So seeing if there's people out there who are doing a lot of that compiling already and thinking through that, and then kind of just following along.
Yeah, I want to mention one more. I feel like there's a lot of developers of tools that have like their own Discord channels, their own Slack channels, and that's just like, it's really genuinely a breeding ground for a lot of ideas in terms of how to address certain challenges using a specific tool. It is you open the floodgates in terms of staying up to date on things. So identify tools and topics that are interesting to you. There's probably a Slack or a Discord channel affiliated with it.
Awesome. Well, thank you so much to all of you again. This is a great event. We'll get the recording out to everyone sometime in the next week. And yeah, you can follow these people on social media, their organizations, and keep up to date with everything that they're doing, all the great work. So thank you again and have a lovely day.
Well, thanks.
Thank you. Bye.